So hello everyone. This is the fourth video of the AI-171 crash, and the purpose of this video is to bring up an interesting incident that happened about 11 years ago in the US with cars. This we all know is the ignition switch of a car, but this particular switch produced by General Motors, used in General Motors cars at that time, in 2014 to be precise, was a really deadly switch because of a lot of fatalities that were associated with this particular switch. Fatalities leading to crashes like the one you see here. And why I picked up this was because I see a kind of chilling parallel between the fuel control switches of the AI-171, which again we all know led to the fatality there in that aircraft's case, and this fatalities of the GM cars, again because of another switch called the ignition switch. So let's look at some figures and numbers to get started. So somewhere in 2014, about 11 years before this AI-171 crash, so GM had to recall about 800,000 of its small cars due to this particular faulty ignition switch, because these switches could shut off the engine while the vehicle was in motion. And the consequence, of course, was that once the engines were off, that would cut off power steering as well, that would cut off braking, and it would also cut off airbags from inflating, all of which meant only one thing, that was a nearly guaranteed fatality. And the company had to in fact keep recalling. Nearly about 30 million cars had been recalled in the next many months, and 124 deaths had to be compensated for. GM had to in fact forfeit 900 million to the US government because they had to defer the prosecution. Not a very nice picture for a company that was having a good name until then. So let's look at the cause of this ignition switch failure itself. I'm just going to highlight the most important point here, which is also relevant to the AI-171. As you can see here, that during extreme moments of vibration, or even in the presence of heavy objects on a keychain, which means you couple more mass to the key there, the switch would change mode from run to accessory without the intent or knowledge of the driver, which was quite similar to what happened in the AI-171's case as well, because the switches just transitioned from the run to cut off without even the pilots noticing it. And as I just mentioned, once this transition happened in the car, the ignition switch from run to accessory mode, everything got cut off to the power steering, the braking, and the airbags. So this, as you can see, when you just look up in the same page here, you see the torque that really GM had to really meet was somewhere between 10 and 20 Newton centimeter, but the actual thing that they found here was that it was less than 10. That speaks of the high lack of adequacy in the design. Right now, let's look at a video here that is from a mechanic who was interviewed by one of the parents of a victim. She was just a 29-year-old pediatric nurse, a very tragic, one of the early victims of this fatal crash.
They wanted to know the truth. No matter what the truth was, they needed to know why their daughter died.
And immediately he knew something was very wrong when he unloaded the data from the Chevy Cobalt's computer.
The engine went from around 2,000 RPM to zero in 1 second. As a mechanic, that's impossible.
What's more, Charlie Miller learned Brooke Melton's ignition switch had somehow moved from on to the accessory position, apparently with disastrous consequences.
And what that told me as a mechanic, that if this switch moved from on to accessory, she had no anti-lock brakes, she had no electronic power steering, and she had no engine control at all.
Miller also noticed how easily the Chevrolet Cobalt's key could be moved from the on position to accessory, with just the slightest jostle, without even knowing it.
It seemed too easy to me. It seemed very easy to me.
Right, so in the second part of the same video, we look at how actually what is involved in the switch, the ignition column especially, and the kind of transition that takes place.
This is an actual ignition switch assembly.
This is how a Cobalt ignition switch works. When you insert the key, it turns what's called the ignition columns. At the far end is a part called the detent plunger, which goes up and down like the top of a ballpoint pen. As it does, it rotates the cylinder that moves the ignition from on to accessory. It's that tiny spring-loaded plunger, a 57-cent piece, that determines how easily the key will move. So what is going on inside the cobalt's ignition switch, causing the older ignitions to let the key slip into the accessory position with such tragic consequences?
Right, so just try to register this last frame in mind because I might talk about it. I'll be talking about it a little later. Now we'll just look at a bit of theory. I thought it's a bit pertinent here to bring in a bit of theory to use the right engineering way to talk about this phenomenon. What you're seeing here is actually something called the participation factor or the modal participation factor of one of the many modes, the jth mode in particular, called gamma j. And you can see that gamma j is dependent on two things on the right hand side, Cj bar, which is actually the eigenvector or the m normalized eigenvector to be precise, m being the mass matrix, and then the f naught, which is what is the vector of excitation. You don't have to, of course, be very closely following what I'm talking about on this slide. It's just just of interest for completeness here. But the point I want to make is the eigenvector is something that's internal to a system, completely dependent on the mass that's coupled to it, the stiffness of the springs involved, and the constraints that are there in the system. And the F naught out there is this excitation is completely external to the system, which is coming from the ambient environment. In the GM car cases, it might have been just a bump or a bit of roughness in it running, whereas in the A171 is obviously the cockpit having an adverse vibration just on being airborne. So let's look at the things in more specifically out here now. In the GM cases, the CJ bar is actually what I call as the rotational mode with the ignition key coupled. That mode can participate very severely with an F naught that's either a dynamic in nature or a quasi-static torque. A quasi-static torque is something that can result for a moment, like just a rough bump somewhere that on the track of the car, the road or wherever it is running. A dynamic one is, of course, where it's sustained for a little longer time. But the A171 cases, we all know that, at least from my second video that I put earlier, the one on 25th July, what I'm strongly believing right now is that this was a bounce mode that was involved here. The bounce mode being the mode that I described in that video. You can go into that video for details. I'm not going to get back to too many details again. And the F naught is the FTD, the transmitted component along the switch axis. So yes, there was in both these switch cases, there is a certain obvious amount of resistance to free movement from one state to another, from run to accessory in the GM's cases and from run to cutoff in the A171 cases, because the A171 does have a strong locking profile. In the GM case also, you could see from the last frame that I talked about in the video, there was a bit of kind of resistance to free movement, but that was inadequate against the environment in which these things were working at that point of time. Right, so now let's look at what is similar to both cases is the thing that snap through. So something called a detent plunger that you heard in that video there. You see that in the top left picture, and the GM cases, this was the one that was really the culprit, having an inadequate margin against trying to snap through from the run to the accessory mode. By inadequate margin, well, what actually I mean is an inadequate margin from a dynamic point of view, having insufficient football frequency there. And the A171 case as well, the same fact holds. The run to cutoff was also because it was not enough. But I have done independent simulations, which I'm not talking about here. The severe adverse vibration kind of severity here in the A171 case was, something that would occur only about 0.43% of the time. So it's not something that you need to often be worried about, but it did happen, unfortunately, in that particular aircraft's case, because there's always nothing is impossible, and in that particular case, it was just a case of crossing all limits, which normally aircraft don't do. All right, so I'll just summarize things with this, just a summary statement out here. So in both the GM ignition switch and the A171 FC switches, it's clear that there were inadequate margins against adverse participation of the respective governing modes with the ambient excitation. So the deadly consequence was just a snap through from run to accessory in the GM's cases and run to cutoff in the AF case. Alright, so I'll leave it with that. Thank you so much for watching, and yeah, good day.